And I am going to be going over day 4 from our Unit 10 notes packet. And the topic for today is continuity. And what's going to happen today is I'm going to give you a function f of x, and I'm going to ask you, is this function continuous at a certain x value? And you're going to have to say either yes or say no. The 3 steps that we have to go through are listed right here. And to show that a function is continuous, you must go through all these 3 steps. If you get the same value for step 1 that you get for step 2, then we can say, yes, the function is continuous. So I'm going to show you graphically what this means before we jump into a problem. Step 1 says that f of a has to exist. So that means if I had a graph at a, I'd have to have a point. F of a would have to exist. So on this thing right here, f of a exists. That's step number 1. Step number 2 says that the limit as x approaches a has to exist. So what that would look like, here's a. Remember, in order for a limit to exist, I have to come from the left side and I have to come from the right side, and I have to meet at the same spot. It's okay if that spot's an open circle, but it has to meet at a certain spot. So this right here was the limit as x approaches a of f of x. This must exist. Okay? But for step 3, in order for something to be continuous, f of a has to equal the limit as x approaches a. So graphically, what that means is if f of a exists, if it's a point up here, then that point, f of a, that y value, must be equal to whatever the limit as x approaches a is of f of x. So if I was looking at this graphically, if something is continuous, the way that I like to think about it is if I can draw my graph without having to lift up my pen, then I'd say, yep, this thing is continuous. On its own, this thing right here, this graph that I drew in the middle, this graph on its own is not continuous because you cannot graph that without having to pick up your pen. Okay? So you've got to be able to graph it without picking up your pen. So let's jump down to some problems here. And the first one, or the directions are the following functions continuous? So as soon as I see that word continuous, I'm going to start going through my 3 steps. And I'm going to number them as I go. Keep your work neat. It says f of x equals 3 divided by the square root of x minus 3, or x minus 4. So my first step is to find f of a. So in our case, our a value is 4, so f of 4. So in step 1, all I do is I go into this function right here, and where I see x, I'm going to substitute the number 4 in. And I'm going to simplify, and I get 3 divided by 0. And in math, that's the only number we're not allowed to divide by. And so when that happens, it doesn't work, and I say that f of 4 is undefined. Now here's a nice little shortcut. If ever you're working through your 3 steps, and if one of the steps along the way does not work, I got undefined, I can stop right there and say that this function is discontinuous. I'm going to write disc for an abbreviation of discontinuous. So are they continuous? Nope, discontinuous. All right, let's try number 2. So number 2 is a piecewise function. Remember, that just means that there's more than one piece. And I'm going to start running through my steps. So my first step is to find f of a. Well, in this problem, a is -1. So f of -1. Now, because it's piecewise, I have to decide which piece to use, the top or the bottom. Well, I'm looking for f of -1. This tells me when x equals -1, the answer is always 0. When x doesn't equal -1, I have to use this fraction. So when x equals -1, my answer is always 0. So I got a number, I'm allowed to keep going. I'll put a little check mark there. So I go to step 2. Step 2 is the limit. Remember step 2 from the top. So I'm finding the limit as x approaches -1. Now I have to write something next to this. Right here I could write f of x, or I could decide which piece to use right now, which is what I'm going to do. Remember we talked about last week, when we're finding a limit, we always use the function next to the does not equal. So I'm going to use x squared minus 1 over x plus 1. And that's what I'm finding the limit of. If you remember from last week, when we find a limit, we try to substitute in first. But if I substitute -1 into the denominator, I end up with a 0 on the bottom, which is a problem. For limits, we are allowed to factor. We're allowed to simplify these things. So I'm going to recopy this limit as x approaches -1. And I'm going to factor to kind of help me solve this limit problem. X plus 1, x minus 1 over x plus 1. I see a common factor, slash them out, and now substitute -1 in to what's left. So -1 minus 1, I get -2. So I got an answer, I put a check mark, and that means I have to go to step 3. Step 3 says that, if I come up top, it tells me that f of a, which was the answer to step 1, has to equal the limit, which was the answer to step 2. And so if you compare these two things, does 0, this is what we're asking ourselves, does 0 equal -2? No. So this thing is going to be discontinuous. Here's how I have to write it. I have to write step 1, which was f of -1 does not equal the limit as x approaches -1 of f of x. Remember we talked about last time how whenever we write limit, we have to put a function next to it. So in this case, f of x. Therefore, discontinuous. In calculus, oftentimes instead of writing out the word therefore, this might seem kind of weird at first, but a little triangle of dots, that means therefore. So f of -1 does not equal the limit as x approaches -1 of f of x. Therefore, discontinuous. And to get full credit, you would have to show all 3 steps with good notation. Okay. Okay, let's move down to number 3. And on number 3, same directions, is this function continuous? So anytime we want to know if it's continuous, we start going through our 3 steps. Step 1, f of -1. Well, let's look at our function. Our function looks pretty similar to number 2, but it's different. So let's use our problem from number 3. When x equals -1, the answer is -2. That's what this bottom part of the piecewise function tells me. So it equals -2. Check. Step 2. Let's find the limit as x approaches -1. Just like before, we said when we're finding a limit, we're going to use the function next to the does not equal, which is the top function. And I'm going to, instead of just recopying this top function right here, I'm going to go ahead and factor it when I recopy it. The numerator factors into x plus 1 and x minus 1. And I'm allowed to do that because this is a limit. And factoring is one of the methods we have. Cross off your common factors. And now plug in. Let's plug -1 in. So -1 minus 1, -2. Check, I got an answer. Now, we're always comparing these two answers. Does the answer from step 1 equal the answer from step 2? Yes, it does this time. And so for step 3, how I would write this is step 1, which was f of -1, equals the limit as x approaches -1 of f of x. So those two things were equal. Therefore, I do my little triangle of dots, continuous. So this was the first one we came across that was continuous. Before I go on to number 4, I want you to think about for a moment graphically what these things would look like. Remember, number 2 and 3 were pretty similar functions to each other. And what they look like, The important piece is -1. And for problem number 2, I know that when x is -1, I have a point at 0. So I've got this point right here. And then I found out from step 2 that the limit as x approaches -1 was -2. And so what it looks like is this. That's what my graph would look like. So if I would have given you this graph and said, is this function continuous at -1? I hope you would have said no, it's discontinuous because I can't draw this without picking up my pen. Okay, so that's what 2 would look like. Number 3 would look like this, -1. So I know that I have a point at -1, -2. And then I also found out from step 2 that the limit as x approaches -1 was also -2. And so this time, this is what it looks like. So if I gave you that graph and I said, is this function continuous? I hope you would say yes, because I can draw this without picking up my pen anywhere. All right, let's try the fourth one. The fourth one is also a piecewise function. And again, I'm going to go through the 3 steps. It's a little bit different though. Problem number 1. I'm finding, and 3 is my value, so f of 3. All right, so it says use the top function in between 0 and 3, but including 3. And use the bottom function when x is greater than 3 and less than 5. So if I'm wondering when x equals 3, what I should use, we're going to use the top. So I'm going to use the top function, which is the square root of x, which is 3, plus 1. Go ahead and simplify that. The square root of 4, which is 2. I got a value. Okay. Step 2 is finding the limit as x approaches 3. Now this one's a little bit different because to find the limit for a piecewise function, if up here on problem 3, if we were given the choice between an equals and a does not equal, we would always use a does not equal for a limit. But this time we're not given an equals and a does not equals. We're given an x is less than 3, and over here an x is greater than 3. Any guesses as to what we have to do? If you are thinking that we have to do it from the left and also from the right, you are correct. I have to show from the left and the right. So from the left, those are numbers that are smaller than 3. I'm going to use this top function because 0 to 3, I use the top. So I'm going to write the function next to it. Notice when I have that word limit in front, I keep the x's in there. And then I'm just going to go in, and where I see x, I'm going to plug in the number 3. So the square root of 4 is 2. So my left-hand limit is 2. Let's find your right-hand limit. For the right-hand limit, coming from the right, I'm going to use the bottom function because x is greater than 3. The bottom function was 5 minus x. And I'm going to go in, and where I see x, I'm going to put in 3. And I get 2. So I need to compare these two values, the left-hand limit and the right-hand limit. And I'm noticing that they're the same. And so I would make a statement over here that the limit, I'm in another room, as x approaches 3 of f of x equals 2. Check mark. Okay, because step 2 is finding the limit. And since the left and the right limits were 2, that means that the actual limit is 2. So what do we think? Is this function continuous or discontinuous? I'll put my step 3 over here. It's going to be continuous. The answer from step 1 is equal to the answer from step 2. So I will write this as f of 3 equals the limit as x approaches 3 of f of x. They're equal. Therefore, which are these 3 dots into a triangle, continuous. Okay, so you must show all 3 steps, especially if you're going to say it's continuous. All right, let's flip our paper over and talk about what happens if it's discontinuous. Okay, on the back, there's a box at the top that talks about the different types of discontinuity. And the first type of discontinuity is a type that we call removable. And removable discontinuity is really just a hole in the middle of our graph. So the only problem with the graph is that there is a hole in the middle of it. This is what something would look like if it was removable. You'd be going along and there would be this hole in the middle, and then it would keep going. But the hole would be the problem that would make it discontinuous. So that's called removable. The next type is called jump discontinuity. And jump is actually just what it sounds like. It looks like this. You're moving along and you stop, and then you jump up to a different y value to keep going. That right there would be representative of jump discontinuity. The third type is called an asymptote. You might also hear this type being referred to as infinite discontinuity. And what that type looks like is there's going to be an asymptote in the middle of your graph, so a dotted line, and your graph might look like this. And so this function is discontinuous because of that asymptote. It's in the way. It does not allow me to draw the whole thing without picking up my pen. There's an asymptote in the way. And the last type is called endpoint. An endpoint is just like what it sounds. At the end of a graph, so let's say that the graph just looked like that. At this endpoint, it's discontinuous. And the reason that an endpoint would be discontinuous is because there's no limit. The limit coming from the left side, there's nothing there. So those are my 4 types, and we have 4 questions we're going to go through based off of a graph. So problem number 1, the first question says, is the function continuous at -1? So look at your graph, and we would answer that question. Is the function continuous at -1? Well, I'm going to say no. Then it says explain. So as I'm explaining, I need to tell which step from the front of this sheet doesn't work. Which step from the first page doesn't work? Well, step 1 was f of -1. So let's do that. F of -1. Yep, that works. That's 2. So that was not the problem. Step 2 of finding continuity was finding the limit as x approaches -1. Well, if you look at your graph, does the limit exist as x approaches -1? No. From the bottom, we're down here, from the left, we're down here, from the right, we're up here. So the limit does not exist. So what I'm going to say to explain is that the limit as x approaches -1 of f of x does not exist. That's where I went wrong. That's why it's not continuous. Part B asks, what type of discontinuity? Well, let's look at our 4 choices. And this one looks like I'm moving along and I jump. So this is called jump discontinuity. And part C says, on what open intervals is the function continuous? So I want to know, where is this thing continuous? I know it's discontinuous at -1, but where is it continuous? I'm going to write an interval, and I'm going to list all my x values. So -infinity all the way up to -1, but it does not include -1, so I put a parenthesis. And then -1 up to infinity. You might ask, why can't we use a bracket right here? That thing is closed in. Well, it's not continuous at -1. And this question was asking, where is it continuous? I cannot include -1 in my answer. Also, the question said what open intervals? Open intervals always mean parentheses. All right, let's try number 2. We've got a new graph there. Is the function continuous at 2? Well, if you look really carefully, there's a hole in the middle of my graph, so I'm going to say no. Explain. So I'm going to start explaining. I'm going to start with step 1, f of 2. So did f of 2 exist? Was there a point? No, there was an open circle. So my reasoning would be that f of 2 was undefined. Step 1 just did not work. What type of discontinuity? So take a minute and look at your choices up top and see what type of discontinuity is this. And it's going to be removable. There's a hole in the middle of my graph is the only problem there. On what open intervals is the function continuous? So negative infinity up to 2, and then 2 up to infinity. And then there's this part D on this one that says, how would you remove the discontinuity? What that means is, what could you do with this problem to make it continuous? Well, if that hole was filled in, it would be continuous. So what we could do is we could define f of 2 being 4. And that would just make this hole filled in by that point. And then all of a sudden it would be continuous. Okay, number 3. Is f of x continuous at 3? And what do we notice is happening at 3 on your graph? Looks to me like there's an asymptote there. So is it continuous? No. Explain. So I need to decide why not, besides the fact that there's an asymptote there. I'm going to think about my steps from the front of the sheet. First step being f of 3. Well, if I asked you what was f of 3, we'd come to the graph, and hopefully you'd notice that there was no point here. Anywhere on 3, there's just an asymptote. F of 3 does not work. It's undefined. So that's my reason. F of 3 is undefined. That's why I'm discontinuous. Also, the limit does not exist, but I'm checking f of 3 first. What type of discontinuity? So look at your choices up top. There's a choice that's called asymptote, and so hopefully this one was pretty simple to choose which type. The type is going to be asymptote. That's our problem. And then this one says, on what open intervals is f of x continuous? Now be careful with this one. Negative infinity. I know it's discontinuous at 3, but if you look at your graph, there's somewhere else it's discontinuous. Where else is it discontinuous? Hopefully you noticed at x equals 0. So negative infinity to 0. There's a hole. That's removable, by the way. And then 0 to 3. And then 3 to infinity. So those are my 3 intervals. All right, last one, number 4. It says, is this function f of x continuous at 1? So I'm noticing that there's a problem. There's a hole in my graph. I cannot draw this without picking up my pen, so I'm going to say no again. But I need to explain. So I'm going to run through those 3 steps that we have to use to decide. Step 1 would be finding f of 1. Well, f of 1 is 2. That worked. So that was not the problem. Step 2 was the limit as x approaches 1. Well, of f of x. If I gave you this graph and said, what is the limit as x approaches 1? Hopefully you would answer negative 2, because for a limit to exist, it just has to come from the left and come from the right to a point, to a spot. And the y value comes to is negative 2. But it's not continuous because these 2 answers are not equal to each other. So what I would write over here is f of 1 does not equal the limit as x approaches 1 of f of x. So that's my explanation as to why it's not continuous. Part B, what type of discontinuity? Okay. This right here is going to have removable at 1. There's a hole. I know that there's a spot up there, but right here I can't draw this without picking up my pen because of the hole. So we call this removable. Removable means there's a hole, and if the hole was filled in, then I'd be able to complete the graph, but the hole's not filled in. On what open intervals is f of x continuous? Okay, well, let's start on the left. We are continuous from negative infinity to 1. So even though there's a dot here, this is all continuous. And then we're continuous from 1 up to infinity. Whoops. Okay. I wanted to actually, before I do part D, I just want to look at 3 for a moment. 3 asks in part B, what type of discontinuity does f of x have? If I was specifically asking you at x equals 3, your answer is asymptote. If I just said, which is what the problem says, what kind of discontinuity do we have? We could say at x equals 3, there's an asymptote, but we did discover over here there was a different type of discontinuity or a different spot, so we technically could add this to our problem. At x equals 0, it would be removable if we were being really specific about every little spot. All right, part D down here, and then we're going to be finished. It says, define f of x as a piecewise function. Okay, so define f of x as a piecewise function. So I need to write a piecewise function. I need to say f of x equals, and it looks to me like there are 3 pieces to this piecewise. There's 3 pieces to this graph. Diagonal line, horizontal line, diagonal line. What I like to do before coming up with each of the functions here is I like to come up with the parameters or the restrictions. So this piece over here that I have in blue is going to be anywhere smaller than -4. So the restriction that I could put on here is x is less than or equal to -4. We'll use whatever function that top one is. Then if I use a different color here, this looks like this is happening in between -4 and -1. So my restrictions here would be -4 less than x less than +1. Notice that I chose to include the closed circle with the top function. Oops. Hopefully you caught this. It should be -4 right here. The or equal to sign could go with this top function or it could go with the middle function, but don't make it go with both. You can pick which one because it's technically, we don't know which graph it's with. And then my last one I will make in purple. This one right here is going to be x values greater than 1. And then I've got to come back to my graph and figure out what equations go with them. Well, for me, this red one's the easiest one to come up with because this red one right here looks like just a flat horizontal line going through -2, and so my equation is just -2. That's all there is to it. My equation is just -2. For the other ones, I've got to come up with the equation of those lines. Okay, what I'm going to do is I'm going to take this line over here, and I'm going to imagine that I have a ruler, and I'm trying to extend this line just to see approximately where it would go if it were to keep going that way. And I'm noticing that it looks like it's crossing over at +3. So if I was going to write an equation in y equals mx plus b, my b is my y-intercept, which looks to be about 3. So +3. And my slope appears to be about 1, up 1 over 1, up 1 over 1. So I would say 1x plus 3. It's going to be my best estimate because I'm not on true graph paper here. All right, then I'm going to do the same thing for this purple graph that's over here. I'm going to imagine extending this down, and I'm going to do my best job to come up with the equation of this one. If I were to put this in mx plus b, it looks like it's crossing at about -3.5 maybe. So minus 3.5. But I need to figure out what my slope is because I'm going to put this in mx plus b. Well, when I try to figure out my slope, it looks like I'm going about up 1 over 1. We're just estimating. Up 1 over 1. Up 1 over 1. I'm going to estimate that to be about a 1x as well, to have about the same slope as this first graph. Okay, so I hope that helped. The lesson for this week is also going to be a Google form. So good luck on that. It will be a worksheet and a Google form.